A continuous, high-pressure water transmission network operates on a massive scale. At this station, heavy industrial pumps force a continuous column of water through 600-millimeter steel pipelines stretching over 17.8 kilometers. Maintaining that flow requires an immense amount of continuous kinetic energy to continuously drive thousands of tons of fluid mass forward against friction and gravity. But that delicate kinetic balance is vulnerable to a single external variable, a sudden power grid failure. When the electricity cuts out, the main pumps trip instantly. In a matter of milliseconds, the mechanical driving force propelling the water forward drops to zero. The pumps stop spinning, but the massive kinetic energy already transferred into that 17.8-kilometer water column does not simply vanish. It becomes stranded within the pipeline network. Without the machinery actively managing the flow, this newly stranded kinetic energy seeks an immediate outlet, turning the transmission system into a highly destructive weapon aimed squarely at its own infrastructure. The first consequence of the pump trip is a high-pressure reverse shockwave, a phenomenon in fluid dynamics known as a water hammer. This diagram illustrates the mechanics. When the trailing edge of the water column hits the stationary fluid at the dead pump, the kinetic energy rapidly compresses. It generates an extreme pressure wave that slams backward down the pipe with enough localized force to easily burst rigid steel joints. Simultaneously, a contrasting threat forms downstream: water column separation. While the water near the pump slams backward, the remaining forward momentum of the water mass further down the line continues traveling away from the source. This physical tear in the fluid creates a localized extreme vacuum within the pipe. This vacuum phase is equally catastrophic. With internal pressure effectively removed, the heavy external atmospheric pressure threatens to simply crush the rigid steel pipeline inward like an empty soda can. The system faces a fundamental physical limitation. Water is virtually incompressible. It cannot stretch to fill the vacuum, nor can it compress to dampen the reverse shockwave. Surviving these opposing forces requires deliberately introducing a highly engineered, compressible buffer into the otherwise rigid network. To build that buffer from first principles, we start below ground level with a heavily reinforced cement concrete foundation. This RCC footing must be heavily engineered. It stabilizes the massive static weight of the steel equipment and the violent, dynamic vibrational loads transferred downward during a surge event. Mounted directly onto this foundation is the Core Containment Unit, a towering 100 cubic meter Class 1 pressure vessel. Standard construction steel is entirely inadequate here. The vessel's shell requires strict metallurgical adherence to boiler quality steel, specifically IS 2002/SA516 grade 70. This specific grade of boiler steel provides the necessary tensile strength to reliably contain extreme internal design pressures, reaching up to 30 kilograms per square centimeter. The vessel's structural geometry is equally critical. Notice how flat end caps concentrate mechanical stress directly at the corners. By utilizing pressed dished ends at the top and bottom, the internal pressure forces are distributed evenly across a curved surface. Surviving a 30 kilogram per square centimeter surge relies entirely on this precise combination of advanced metallurgy and geometric stress distribution, rather than simply welding thicker plates of steel. Structural integrity only handles the kinetic threat. The vessel must also be engineered for chemical and environmental survival over a decades-long life cycle. The interior surface of the vessel requires a strict internal coating specification, a precise 250-micron application of food-grade epoxy. This continuous epoxy layer performs a dual function. It completely isolates the vulnerable inner steel from continuous water corrosion, while guaranteeing zero chemical contamination leaches into the municipal water supply. On the exterior, the steel is treated with a specialized 150-micron external metallic aluminum paint. This reflective metallic finish acts as a thermal and ultraviolet shield, reflecting environmental heat away from the highly pressurized and thermally sensitive internal environment. Wrapping around this treated cylinder is a heavy structural maintenance architecture, consisting of access catwalks and vertical safety cage ladders. These access points are fabricated from industrial IS-2062 mild steel structural brackets and lined with diamond-patterned checkered steel floor plates for traction. A comprehensive EPC project requires designing a system capable of withstanding constant environmental exposure and facilitating safe human maintenance long after the fluid dynamics equations are solved. To integrate this vessel back into the main water transmission line, a 600mm pipeline branch is bolted directly to the base of the air vessel via heavy flanged joints. This diagram shows the inline non-return valve between the pump house and air vessel. Under normal operation, forward flow holds the internal flap open. When power fails, gravity and reverse pressure slam the flap shut within milliseconds. This valve acts as a one-way physical diode. It actively blocks the high-pressure reverse shockwave from traveling any further upstream. If this non-return valve fails, the returning pressure wave would bypass the protection system, slam directly into the delicate pump impellers, and physically tear the station apart. By isolating the fragile pumping machinery, the non-return valve successfully barricades the line, forcing the entirety of the destructive surge energy to divert upward, directly toward the waiting air vessel. Despite its massive size and structural strength, this steel containment vessel is entirely useless as a shock absorber if it is completely filled with incompressible water. Compressibility is provided by an active pneumatic control system. This features a 1 cubic meter air receiver tank linked to the top of the main vessel via thick stainless steel 316 header pipes. The engine driving this pneumatic system is a pair of constantly vibrating industrial air compressors. These compressors operate under rigorous specifications, forcefully pumping 50 to 60 cubic meters of air per hour into the upper sealed chamber of the vessel. They work continuously to maintain a precise 30 kilograms per square centimeter of pressure. This guarantees a mathematically exact air-to-water ratio inside the tank at all times. The surge vessel is not a static water storage tank. It is an actively calibrated pneumatic spring, kept fully primed to catch a catastrophic hydraulic load. With the foundation poured, the metallurgy verified, and the pneumatic system pressurized, the complete unit sits silently in the bright outdoor pumping station. Then, the power grid fails. The pumps trip, and the hydraulic transient begins its path of destruction. Blocked by the non-return valve, the initial high-pressure wave slams into the base of the surge vessel, forcing massive volumes of water violently upward into the tank. As the water level rises, the carefully maintained volume of compressed air at the top is violently squeezed. It acts as a giant pneumatic cushion, smoothly absorbing the immense kinetic shock that would have otherwise burst the pipeline. Within seconds, the dynamics invert. The rebounding low-pressure wave pulls away, creating a severe vacuum risk inside the main transmission line. Now, the highly compressed air inside the vessel rapidly expands. It forcefully pushes the stored water back down into the pipeline, physically filling the void and preventing water column separation. Further down the network, 16.1 kilometers away, a final failsafe activates. Localized pressure drops occur. This cast steel vacuum breaker valve springs open, sucking in massive volumes of atmospheric air to prevent the surrounding pipe from collapsing inward. The continuous survival of vast, multi-kilometer hydraulic infrastructure is achieved by countering immense destructive kinetic forces with precisely engineered pneumatic elasticity and unyielding mechanical containment.